Welcome back to Beyond the Known, everyone. This is our fifth deep dive in the Edge of Reality series.
Where we really push the limits of the known.
Exactly. And today, we're jumping headfirst into something truly mind-bending. Quantum weirdness.
Yeah, if you thought our previous topics were out there, well, buckle up. The research today takes us somewhere the usual rules just don't seem to apply.
For those who've been following along, we've already been down some strange paths in this Edge of Reality series. Maybe a quick recap.
Good idea.
Yeah.
Help set the stage for today's weirdness.
Okay, so first we did exploring the placebo effect. And that was all about, the power of belief.
Right, how your mind can actually change your physical state. We saw things like endorphin release, dopamine.
Yeah. Saline injections acting like morphine. Those sham surgeries having real effects. It was wild.
And the nocebo effect, too, the downside. Plus, those open-label placebos really makes you think about mind over matter.
It really does. Then, deep dive number 2, we went big. The multiverse theory.
Ah, yes, the idea that our universe might just be one of, well, maybe infinite others.
We touched on eternal inflation, bubble universes, the whole many worlds idea from quantum mechanics itself.
Which kind of ties into today, actually.
It does. And the simulation hypothesis, which we came back to later, Smolin's fakened universes. String theory. It really stretched the idea of reality.
Definitely puts you in your cosmic place, or lack thereof.
Then we turn inward for the science and significance of dreaming.
From Freud and Jung's ideas about the unconscious and symbols.
Right, to the more modern stuff like the activation synthesis hypothesis, how dreams help with memory consolidation. Remember that Alpine racer study?
Oh yeah, the neural replay speeds and emotional regulation, threat simulation theory.
And lucid dreaming, trying to signal from inside a dream and just, why we remember some dreams and not others.
It showed that dreams are probably way more important than just random brain noise.
For sure. And then, most recently, we tackled the simulation hypothesis.
Asking that big question, could this all be a giant computer program?
We looked at Bostrom's argument, but also the criticisms, like Hassenfelder pointing out the sheer difficulty of simulating Einstein's physics.
Yeah, the computational power needed is just staggering. We also covered substrate independence, sparse rendering, and the fact we don't really see glitches.
It definitely made you question what real even means.
It did. A perfect lead-in, actually.
Exactly. Because after all that, you'd think we've hit peak strange.
Mm-hmm.
But quantum weirdness, this happens at the smallest scales. It's where our everyday understanding of physics just kind of breaks down.
It's fascinating, isn't it? The physics that works so beautifully for planets and apples, it just falls apart when you get down to atoms and electrons.
So this idea of classical physics breaking down, it makes a kind of sense, right? Our normal physics is based on what we can see and touch.
Exactly. Classical physics makes assumptions based on our macroscopic world, and those assumptions, well, they don't necessarily hold water at the quantum scale. Think about how we see things.
Light, usually.
Right. Light bounces off an object, hits our eyes. But what if the messenger, the light particle, the photon, has enough energy to seriously disturb the tiny thing you're trying to look at?
Ah, okay. So the act of looking changes the thing you're looking at.
Precisely. The research uses a good analogy. Imagine trying to find a billiard ball on a frictionless, weightless table, but the only way to find it is to shoot another billiard ball at it.
The collision would send the first ball flying. You wouldn't know where it was.
Exactly. You disturb it fundamentally. And at the quantum level, our messengers, like photons, do significantly disturb the particles we're trying to measure. The observation isn't passive.
It becomes part of the experiment, part of the interaction.
Correct. And there's a neat parallel with relativity here, too. You know how relativistic effects aren't obvious in daily life because the speed of light is so incredibly fast?
You don't notice time dilation driving to the shops.
Right. Well, similarly, quantum effects were hidden for ages because light, on our scale, seems so continuous, so fine-grained. The weirdness was too small to see easily.
Until our experiments got sensitive enough, I guess.
Exactly. And just like assuming space and time were absolute caused problems that led to relativity, assuming the world was fundamentally continuous at the smallest scales, eventually led to contradictions that forced physics to accept a discontinuous quantum structure.
Which brings us right to maybe the weirdest part. Wave-particle duality.
Ah, the central paradox. Is reality made of tiny bits, particles? Or is it flowing fields, waves?
And quantum mechanics says, kind of both, depending on how you ask.
That's pretty much it. It's baffled physicists for a century. These quantum things, photons, electrons, whatever, they show wave-like behavior, like interference patterns.
Like ripples in a pond crossing over each other.
Exactly. But they also show particle-like behavior, like being absorbed at a single point, a specific location.
So it's not that they are one or the other, but they can appear as one or the other.
Yes, and crucially, how they appear depends on the experiment, on the observer, on the questions you're asking. Set up to detect a wave, you find a wave. Set up to detect a particle, you find a particle.
It's like reality itself is responding to our investigation.
In a sense. And the research rightly points out the words wave and particle are just metaphors from our big world. They probably don't capture the true nature of whatever these quantum entities really are.
The history is interesting, too. Didn't Planck sort of stumble onto this with blackbody radiation?
He did. Trying to get a formula to work for how objects glow when heated, he had to sort of patch together equations that treated light as waves and particles, introducing the idea of quantized energy.
And then there was that father and son, the Thomsons.
Oh, that's a great story. J.J. Thomson won a Nobel for showing the electron was a particle. Years later, his son, G.P. Thomson, won a Nobel for showing the electron behaves like a wave.
Wow. Talk about illustrating the point.
Absolutely. And you can imagine the pioneers like Schrödinger and Heisenberg really struggling. They were trying to use familiar, visualizable concepts from classical physics.
But they just didn't fit this new quantum world.
Right. Schrödinger's famous wave function wasn't even in normal 3D space. It lived in a mathematical configuration space. And even when Max Born said the wave function represented probabilities,
it still didn't explain why making a measurement suddenly forced one specific outcome out of all those possibilities. The collapse of the wave function.
Yeah, exactly. Which leads us squarely into the role of observation and measurement. It's not just looking, it's doing something.
Heisenberg's uncertainty principle.
Right.
That comes in here.
It's fundamental. Heisenberg's thought experiment with the gamma-ray microscope really nailed it. To see an electron's position precisely, you'd need a high-energy gamma ray.
But hitting the electron with that much energy would totally change its momentum, wouldn't it?
Exactly. The act of measuring position precisely makes the momentum uncertain, and vice versa. You can't know both perfectly at the same time.
Like trying to grab smoke. The harder you try for one thing, the more the other slips away.
A good way to put it. And the research highlights an ambiguity, too. When we say we determine a property, what do we mean? The initial interaction, or the final click on our detector?
Because the particle has to interact with our detector after the initial measurement interaction.
Precisely. The thing we observe is the result of a chain of interactions. And properties like momentum, we don't see them directly. We infer them from how they affect our instruments.
Like seeing the interference pattern tells us about the wave-like nature, which relates to momentum through de Broglie's equation.
Correct. And that momentum is relative to the observer, too. Your frame of reference matters.
It all feels so interconnected. It makes you wonder. One source even suggested our tendency to see the world as separate objects in space might be just how our brains evolved to cope, and maybe that limits how we think about quantum reality.
It's a deep thought. Our cognitive tools were shaped by the macroscopic world. Are they the right tools for the quantum level? Maybe not perfectly.
Okay, let's move on to quantum properties and entanglement. This is where it gets really weird, right? The spookyaction.
Einstein's famous phrase, yes. It starts with the problem of identity. If quantum particles, like two electrons, are truly identical, perfectly indistinguishable, does it even make sense to call them particle 1 and particle 2?
Like two identical copies of a file on a computer. Are they really separate things?
Kind of. The term particle might be misleading if it implies individuality from the start. Maybe it's better to think of fundamental identical units, like units of currency. The value is identical, even if the physical coins have tiny scratches.
Okay, so how does entanglement fit with this identical nature?
Entanglement shows how our normal ideas of part and whole break down. You can link two or more particles so they become a single system, described by one shared quantum state. They're inseparable, even if you move them miles apart.
And measuring one instantly tells you something about the other, no matter the distance.
That's the core of it. Measure the spin of one entangled electron, say you find it spin up. You instantly know the other one must be spin down to conserve the total spin, even before you measure it.
Faster than light.
Well, it seems like instantaneous influence. This is the spookiness. The correlation is instant, but you can't actually use it to send information faster than light. That's a key point.
Okay, so it's a correlation, not communication.
Right. And the research contrasts this with classical correlations, like our billiard balls. After they collide, their momenta are linked. Measuring one tells you about the other, but measuring one doesn't change the other instantaneously.
But in quantum entanglement, the measurement does seem to affect the distant partner instantly.
It appears that way, yes. And experiments have confirmed this spooky correlation over huge distances, even using linked superconductors in some cases.
So it's real, even if it's weird.
Absolutely. Though, interestingly, from a pure wave perspective, entanglement is maybe less weird. A single spread-out wave naturally has correlated properties at different points.
So the mystery isn't the correlation, but why the wave collapses to a point when measured.
Exactly. It brings us back to wave-particle duality again, and it's worth remembering this coherence, the state needed for entanglement, often needs to be carefully created and shielded. The natural tendency is decoherence interaction with the environment messes up these delicate quantum states.
Okay, so we have discreteness, interconnectedness. What about this tension between continuity and discreteness itself?
Another fundamental issue. Our classical intuition loves continuity. The idea you can always measure something more precisely, divide things infinitely.
But at the quantum level, we hit limits, right? Quantization.
Exactly. Energy, angular momentum, other properties come in discrete packets, or quanta. You can't have any old value, only specific allowed values. This fundamentally challenges continuity.
And it messes with classical determinism, too. The idea of predicting the future perfectly if you know the present conditions.
It does. Because of the uncertainty principle, you can never know the initial conditions perfectly. So perfect prediction is impossible. Quantum mechanics gives you probabilities, not certainties.
So the future is inherently fuzzy at the quantum level.
The predictions are probabilistic, yes. Though some interpretations argue the uncertainty is statistical about the limits of our knowledge over many measurements, not necessarily about pure randomness in each single event.
That's subtle. Maybe determinism is just a feature of our models, not of reality itself.
That's a definite philosophical position some physicists take. Randomness might just mean we haven't found the pattern yet, or we can't predict the pattern precisely.
And this even calls into question simple ideas, like saying a single photon is emitted. How do we know it's just one, without assuming it's a particle to begin with?
Right. The measurement itself relies on the concept you're trying to prove. It's a bit circular, highlighting how deep the conceptual challenges go.
Okay, wow. Let's try to ground this with some key examples. We've talked entanglement and uncertainty. What about superposition?
Superposition is classic weirdness. A quantum system can be in multiple states at the same time, like a switch being both on and off simultaneously.
Until you measure it, and then it chooses one state. Like Schrödinger's poor cat, both alive and dead, until the box is opened.
Exactly. And then there's the double-slit experiment. We touched on it, but it's worth revisiting.
Right, firing single particles like atoms at two slits.
And you get an interference pattern on the screen behind, like waves would produce, even firing them one at a time.
How? Does each particle somehow interfere with itself? Does it go through both slits?
It seems like it. It acts as if it's aware of both paths. But the killer part is if you put a detector at the slits to see which slit the particle goes through.
The interference pattern vanishes.
Poof! Gone!
Yeah.
The particles then just act like normal little bullets going through one slit or the other. The act of observing the which path information destroys the wave-like superposition.
Just looking changes the reality. That's deeply strange.
It's at the absolute core of the quantum mystery. It suggests the observer isn't separate from the observed system at this fundamental level.
Okay, but this isn't just theoretical weirdness locked in labs, right? This stuff actually powers things we use.
Oh, absolutely. Quantum mechanics is fundamental to so much modern technology. Lasers, for instance. They work because of a quantum process called stimulated emission.
So laser pointers, barcode scanners, fiber optics for the internet.
All quantum. And quantum cryptography uses quantum principles for secure communication. GPS relies on super accurate atomic clocks on satellites.
And atomic clocks are governed by quantum physics.
You got it. Then there's fluorescent lights, MRI machines for medical scans. Even the heating element in your toaster involves quantum effects in material.
It's everywhere. Even in biology. I heard something about birds navigating.
Yes. There's active research suggesting birds might use quantum effects, possibly entanglement in molecules in their eyes, to sense the Earth's magnetic field for navigation.
Nature might be using quantum tricks.
It seems possible. And then you have macroscopic quantum effects, things you can almost see. Superconductivity electricity flowing with zero resistance at low temperatures.
And superfluidity liquids flowing with zero friction.
Exactly. In superconductors, electrons pair up and act as one giant quantum wave. Magnetic fields can't even get inside them. Superfluents can climb walls, flow through tiny cracks. Totally non-classical behavior on a large scale.
In Bose-Einstein condensates, the fifth state of matter.
Right. Cool atoms down near absolute zero, and thousands or millions of them can merge into a single quantum state, acting like one giant matter wave. You can see quantum interference effects with the naked eye, almost.
NASA's Cold Atom Lab on the space station studies these, right? Taking advantage of microgravity.
Precisely. Microgravity lets them observe these states for longer and in different ways than on Earth.
It's amazing how these effects scale up sometimes. There was also that more unusual source, the dyslexic artist theory, about light interaction.
Ah, yes, quite a different perspective. They propose that interacting with light is sort of an ongoing creation process. We participate in forming new photons or oscillations with each interaction, each now.
And linked it to charge exchange, maybe even in biology or across space.
Yeah, connecting light interaction, charge movement, maybe cell membranes, even plasma in space. It's a very holistic, process-oriented view, less about fixed particles and more about continuous interaction.
Interesting food for thought. Now, with all this weirdness, physicists are trying new ways to think about it, right? Using diagrams.
Yes, that's a really active area. Instead of just relying on the complex maths, they're developing diagrammatic approaches to map out causal links and information flow in quantum processes.
Trying to get a more intuitive picture of entanglement, maybe?
That's a major goal. Many interpretations of quantum mechanics force you to accept really radical ideas, faster than light influences, many worlds, things that violate common sense.
So the hope is these diagrams might lead to a more palatable realism, something closer to our classical intuition, but still fully quantum.
Exactly. Trying to build realist models by carefully distinguishing what's a causal physical link, often shown vertically in these diagrams, versus what's a subjective inference or knowledge gained by an observer, often shown horizontally.
Using visual tools to bridge the gap between the quantum math and our understanding.
That's the idea. And speaking of understanding, Carlo Rovelli has a really interesting take on why it all seems so weird.
What's his view?
He suggests the weirdness comes from our assumption that objects have intrinsic properties independent of anything else, like a ball is red all by itself.
But quantum mechanics might be telling us properties only exist in relation to other things.
Precisely. Things only have properties through interaction. His analogy is a chair. It's a chair because we can sit on it. An interaction. It's red because of how light interacts with it and our eyes' interactions.
So maybe at the fundamental level, all properties are relational. There are no inherent standalone properties.
That's Rovelli's proposal. And if we could really internalize that relational view, maybe quantum mechanics wouldn't seem so paradoxical or weird anymore. It would just be describing reality as it fundamentally is, a network of interactions.
That's a huge shift in thinking. Not objects, but relationships.
It really is. It reminds us that our everyday intuition, built for our scale, might not be the right guide for the fundamental nature of reality.
So, wrapping up this deep dive, quantum weirdness truly shows us a reality far stranger than we experience daily. It shakes our foundations, space, time, causality, what an object even is.
And the weirdness really seems to stem from applying our macroscopic concepts in language where they just don't fit neatly.
Key takeaways, though. Wave-particle duality, the active role of observation, the bizarre connection of entanglement, and the probabilistic nature of it all.
And critically, it's not just abstract theory, it's the bedrock of so much technology we use every day.
Absolutely. The quest to understand it pushes physics and our grasp of reality constantly. So many unanswered questions remain.
It's a frontier that keeps expanding, challenging our deepest assumptions.
So, something for everyone listening to think about. What part of this quantum weirdness grabs you the most? What do you find most confusing or fascinating?
And does that idea of a fundamentally relational reality change how you see the world?
Big questions, definitely worth pondering.
It's a field that really stretches the imagination.
Well, thank you so much for joining us on this journey into quantum weirdness today. We really hope you keep exploring this incredible area.
Yeah, there's always more to learn, and we hope we've sparked some curiosity.
And if you enjoyed this deep dive on the edge of reality, please do like, follow, and subscribe to Beyond the Known, We'll have more explorations into the mysteries of the universe coming your way.
We really appreciate you being with us.